Good morning, everyone. My name is Caro Campos. I'm a developer at the Conan team. I'm sure you've heard about this amazing packaging tool. And today, I'm going to talk to you about modules. In particular, I'm going to start with a brief introduction about C++ modules and their advantages and compared to header includes. The focus is going to be on name modules. You may have heard about importable header units. Those are not in the scope for this session. And what I want to talk about today is, in particular, if I want to use a library that is available as a module, how do I do it? How do I go about packaging it? And is that my concern as a developer? Is that the concern of the maintainer of the library? How does that work in practice, and what are the implications and the current limitations as well? And as you will find out today, there's still a lot of work both in the compiler side and the tooling side, and even the libraries as well. So let's get to it. You may be very familiar with the include directive, which is basically a way of telling the preprocessor that happens right before compilation to include the contents of the specified file at the point where the directive appears. So that file that is probably four lines code, yeah, I think so, excluding blank lines, it expands to about 350,000 lines after that is replaced. And this is what we're all familiar with at the moment. If the compiler is not able to find that file, if you miss the include directive there, what's going to happen is the compiler is going to tell you when it gets to that line, use of an undeclared identifier. That's what's going to happen. So the idea with modules, and we're going to see later, is to replace that include with an import. And at the moment, how does the compiler resolve those includes? There's one of two ways. Either the compiler knows to look in some places by default, right? This can be typically because when the compiler is built itself, we hardcode those paths, and that's what usually happens on Linux, and that's why places like user include are going to be looked into, or the actual directories where the standard library headers are relative to the compiler executable. It could be relative to the including file if we use in double quotes rather than the angle brackets. Or more typically, we can pass include flags to the compiler to tell help, to hey compiler, to resolve these files, please look in these directories, right? We're used to that, although I would say that these days we don't necessarily manually pass flags to the compiler. Typically, this is handled by the build system, like with a find package in CMake or something similar. So this is what happens when the compiler is unable to find the file, and this is what happens when the compiler is able to find a file where it just doesn't show any errors at all. And this is what I was mentioning earlier. What you're typically likely to do, rather than pass that flag directly to the compiler, is just do a targeting libraries in CMake or something similar, where it's done for you under the hood. So what does a typical library package for FMT would look like, right? And this is what would happen if you install FMT with any of these tools. It's going to trigger a process by which these files will be produced or downloaded from somewhere, and they will be in your file system. And so we have the header files. We have the library file if FMT was built as a library, and it could be a static library or a shared library. And also as well, especially in the case for FMT, we may have the FMT config CMake file, which has all the sort of meta information for CMake to consume it. And that's pretty much the process in any of these packaging solutions. And that's what the package looks like today. So focus for today is what would consuming or FMT as a module would look like, and what are the implications. I've done this before. Yeah, sorry, this is what I just explained. Modules. So this is what it looks like with an include, and this is what it would look like with an import statement. And this is what happens if I try to compile a file and I don't tell the compiler where to find the module. It would just say, I cannot find that. How do I solve that? But first, let's discuss why would we use modules in the first place. And reading all the background with modules, you may have heard mostly the last one, which is the improved build times. But I think there's a lot of advantages when it comes to isolations, right? There's a lot of niggles that we're used to when it comes to the preprocessor. At the moment, you can, by defining a macro before the inclusion, you can affect what happens in the included file, or the other way around, you can include something that changes what happens for the rest of the code, and the order of the includes may matter depending on which order you place them. That does not happen with modules, right? So it actually gives you better isolation when you import things, as well as the potential for improved build time. So I'm going to show you an example. Some of you may be very familiar with this, and this is from a blog post. I think it was summer last year, where developer was facing this compiler error, and I don't know if you can see it there, but on the second line where it's complaining about error C2589, it's just hard to reason what's going on, right? And what they were doing is this: they were including Windows at H, and then they were including the flat buffers header file. This is a very common thing that's been hunting us for decades, I believe, and it's because the Windows header defines as a macro both min and max, and somewhere in the flat buffers header or any of the files included by it, that were being invoked. So what you need to do is actually, you see the examples here of how including the Windows header influences how the flat buffers header is included. And the solution to this is actually defining something before the Windows header to actually solve this, and that's what would cause this problem to go away. And what I found interesting is that despite the fact that we've been aware of this for, like I said, probably close to 2 decades, if not longer, this is still an issue that's happening. If you can see the date, that's August 2023. So developers even recently are facing this, I would say on a daily basis probably. Whereas this would not be a problem with modules. So as I showed you earlier, the compiler needs to know where to find the module. But what does that actually mean? In this particular case, if I'm using Clang, I need to tell Clang where to find the module file for the name module FMT. That's a way of doing it. So I tell -f module file FMT, and then the path to this magical file, which is called fmt.pcm, which I'll get to it in a second. And that's just the different ways in which different compilers can achieve the same thing. So I just show you an example with Clang, where you can tell it specifically the module file for the name module, or you can give it a path to a folder that contains these files based on the name, or you can tell MSVC something equivalent. GCC is a little more limited in this particular case. It allows you to pass a module mapper, which could be a server, which could be a file in a file system that has the equivalences between the module name and the file. But there's only one module mapper that you can pass. So I found some limitations with that, but it does work as well. So let's get to it. The module interface unit, which is that file, is the file that has the export module FMT statement. This needs to be translated first by the compiler in order to produce what is called the build module interface or binary module interface, depending on which documentation you're reading. And this file is the binary representation that the compiler needs to actually find in order to resolve that import, right? Every compiler is using a different extension for this file. I don't think it's particularly relevant. Just so it's good to be aware of them. And the module interface unit as well. Some compilers use, like MSVC, they use IXX as an extension. Clang uses CPPM. These days, it doesn't matter as much. And we know for C++ there's a lot of extensions used anyway. So that's just how it is with modules at the moment. So an interesting thing about the interface units is that 2 files can be produced when invoking a compiler. One of them is the build module interface, which is going to be needed by the compiler to resolve the imports on whoever, when translating the units of the files that are doing the import. And then an object file, which if you have implementation in this file, the implementation will be in the object file, and then you can link it into a library. So the concept of modules is a bit of orthogonal to libraries as well. You can still have libraries, whether they're static or shared. And then the question is, you would no longer use headers with those libraries. You ship something else. What that something else is, we'll see in the next few slides. And as I mentioned, that file, that's what you would link into a libfmt.so or just as a static library as in this slide. So in order to produce our executable, let's say on the left we have the FMT module that does the export. On the right we have a main executable that only does a hello world by importing FMT. So when we translate, let me see if I can get there. When we translate main.cc, the compiler is going to need fmt.pcm to exist in order to create the main.o. And then you can just link directly both main.o and fmt.o into the hello world executable. That's how it works. Or if you previously linked fmt.o into a shared library, then you link against the shared library. I mentioned earlier that one of the biggest hopes for modules is improved compilation times. At the moment, what could happen here, let's say we have a project, and on the left we have all the C++ files, and all of them are doing #include fmt/core.h, right? So there's no dependencies between these files at all. So what could happen is, or like typically happens in a build system like CMake or something like that, is that all of these could be compiled in parallel. We can have parallel invocations to the compiler, with the downside that what's happening is that if you are including fmt.core, and as I showed in one of the first few slides, this was actually 350,000 lines of code, the compiler is parsing the same file over and over and over again, right? One of the hopes with modules is that you only do that once, and then that PCM file, the BMI, the build binary interface, is an internal representation that is really fast for the compiler to load. So we would only do that parsing once, and that's where the compilation build times improvements would come. And I'll just explain this. However, this introduces a dependency now. If all of these files now switch from doing include fmt/core.h to doing, from include to import, right? You cannot compile any of those files until you have translated fmt.csx to produce fmt.pcm. So now we've moved from a place where all of the source files that we have could theoretically be compiled in parallel by having a compilation order. And in order to see whether this improves build times or not, I have an example from a blog post from Tristan Brindle from last year, where if you compile a file that does include flux.hpp, in this particular case, it took 300 milliseconds. And if you move to do an import flux, then compile the same file took 14 milliseconds, right? I tried to, these are not to scale, but I tried to do my best, but the numbers were correct in the test that I did. Now, the overall compilation times, those 14 milliseconds do not include the time to build the BMI for Flux, right? But the idea is that if you have a large project and you have the same files that are being included over and over and over, if we move to modules, we would see the benefits, right? But in this particular case, if we were fair and we said the entire project requires building the BMI for Flux, then probably we need to add to those 14 milliseconds, we need to include how long it took to generate that BMI. And that particular project may not be quicker to build. This is something that we may see in larger projects as well. Now, your imports can have imports, and I suspect that over time this is likely what's going to happen. So if I have my application that imports foo, but actually the foo module imports two other modules, then the compilation order will matter here. I can probably compile those first in parallel because there's no dependencies between them and they don't have dependencies in other modules. Then I can compile foo cppm to generate the BMI for foo. And once I have the BMI for foo, then I can actually compile my app.cc. So if we were using includes, most likely we would be able to compile these 4 files in parallel. Now I have three steps. So This is actually a problem for build systems and other limitations. So now the build order cannot have any cycles between them. So you cannot have circular dependencies between the modules that you're importing. And there's a specific order in which the files need to be compiled in order to get the end result. So as a bit of a summary, when we're using include files, we can compile several files in parallel, which is good for speed. But if the same header files are being included in many translation units, then there's a chance that we're actually doing the same work over and over. And as I mentioned earlier, there's a lot of downsides with the preprocessor because it can influence the code after the inclusion, or you can influence the code that you're about to include by defining macros. Whereas using import, there's a chance that we can do that work only once and then reuse that work for other translation units. There's better isolation, but the downside is that now we have a build order that we have to respect. We have to derive that build order before getting a build. So when it comes to the build order for modules, there is something called dependency scanning. So it would be very hard to do, but it would be possible to do if you know which files are importing which modules. You can probably code it in your build system, whether you're like manually rolling your make files or in CMake. You would have to tell CMake very, very carefully which files need to be compiled before others, what the order is. So this would be very tedious, and I would imagine that the source files, you can change over time what modules are imported or not. So I don't think duplicating the logic of who imports who in the make files is the best thing to do. So this is what the tooling community has come up with, which is rather than having the compiling everything in parallel, now we have to ask the compiler, I have this file that I need to compile. What modules does it depend on, right? And what modules does it export if it does? And with that information on the first pass, then we can compute the right build order. Now, the last bit that we need for this to work is typically on a make file or a Ninja file generated by CMake. The build order is already known at generation time. But with this, we need now to run that first pass ahead of the compilation of the files, and then reorder the build order on the fly based on the information that we had. So that's why this was added to Ninja, I believe, by the CMake developers in order to support this method of reordering the build on the fly. And this was actually added to CMake, I think it was released last December in CMake 3.20.28. And that method of describing, of dependency scanning, asking the compiler, hey, can you tell me which modules do you depend on per source file and which modules you export if you export any. That's available in Clang 16, in MSVC from Visual Studio 17.4, in GCC 14, which was just released, I think, a little over a month ago. And CMake, you're going to need version 3.28 for two things. This is the version of CMake that actually had module support, fully functional, which supports dependency scanning, assuming I'm using those compiled versions, and the support for imported targets that have modules, export modules, that I'll get to in a minute. And we have an additional limitation is that you have to either be using a version of Ninja that's 1.10 or newer. MS Build, this will not work with make files because they don't currently support the mechanism of reordering the build targets on the fly. And actually what I found is that dependency scanning works really well. And this is an example of the C++ ecosystem coming together to support a new feature. We needed collaboration from the compiler because we need the compiler to give us the tooling to actually give us that information, the modules that are imported and exported. And this is done with a JSON file that is described in those papers. We need the build system, in this case CMake, to actually be able to coordinate those invocations to the compiler based on the sources that it knows about. And we also needed the Ninja to support reordering the build based on the information. So this is huge. It actually took a lot of coordination, and it was really nice to see the discussions happening in a different, whether it's mailing list or issue trackers, and how things were coming together. But when you actually look at this and compare to consuming libraries that provide include files and the library file, the binary library file, is that there's an important constraint here, that for everything you import, the source that has the module interface unit needs to be visible to your build system, right? It's no longer the case of I have an include folder, I pass an include flag, and that's it. Now you have those files that are presumed to be provided externally are going to need to be visible to your build system. So one of the biggest limitations initially is that how does consuming a pre-built library look like if you don't have that file? Or what do we need to do? We have to do an additional step here. The compiler needs to be invoked whenever a library, whenever you are importing a library that exports a module, right? So I'll show you how that works in a second. So let's say we have a very simple CMake project. On the left, we have a hello FMT that does exactly what I was showing, that hello over there. We want import FMT, and we want to call find package. We want this to work, right? This is what we would expect to work if instead of import, we have an include. So as I showed earlier, this is what the FMT package looks like today. What would it look like if it is packaged as a module library? And this, we don't have to go too far, because just this week, and I think it was actually Tuesday this week, right? FMT version 11 was released, which supports modules. And this is roughly, if I extract all of it from the CMake list, this is roughly what it looks like. When building the FMT library, we need to tell CMake that fmt.cc exports a module. So this is actually a module interface unit. And we also need to tell CMake that this requires, at the very least, C++20. And that's pretty much it. CMake knows from this information, if you're using CMake 328 and one of the build systems mentioned here, the CMake needs to do dependency scanning. So if somewhere else in your project you link against FMT, the FMT target, then it's going to work. Dependency scanning is going to kick in. This file is going to be compiled to produce the BMI before compiling the files that do the import. So I encourage you to try this. It was actually released this week. Remember, you need to be using CMake 328. And in this case, I saw that it requires Ninja. I think I need to open an issue that it should also support MS Build.
Sorry, you lost me. Why do I need to know the dependency when I cannot recompile FMT any? I cannot do anything.
Correct. So I'll show you exactly. I'll show you exactly what happens. This happens under the hood, right? So you will not be recompiling FMT, but what the build system needs to do is generate the BMI for FMT. And I'll show you why. So this is, let me move this away, sorry. This is the way we used to packaging libraries today, right? And I'm sort of classifying these in 4 different ways. We either adopt the sources in our project, so we don't actually package anything. We just say, okay, I'm going to copy the sources of FMT into my project and have my build system deal with it. It could be packaged as a static library, as a shared library, or we could have a header-only library where all I bundle is the header files. And I know FMT in this case actually does support a header-only library. But in this case, for illustration purposes, I'm assuming that in both cases we have a binary library. So when it comes to module libraries, how will we do this? We can, as the first option, we can adopt the sources in our project, or we can consider bundling the BMI alongside the compiled library of FMT, whether it's shared or static. Or we can bundle the library, but also the sources for the FMT module interface unit. And remember, it doesn't have to have any implementation in it. On the important side, the compiler only needs to know the declarations. Or how about module only? How about I only give you the sources, and I give you nothing else, how does that work compared to header-only files? So if we were to do no packaging and we were to adopt the sources in a project, this is a way of doing it with fetch content declare in CMake, but you can also copy the sources and do add subdirectory. You can copy the sources and add your statements in your own build system just to build the relevant files. And as long as your build system supports dependency scanning, this would work. Your build system would know, it would compile a BMI before the importers, and that's how it would be done. So this actually does work. What I tried to do, just as a sort of curiosity experiment, is bundle the BMI, right? The BMI is a binary file, it's specific to the compiler. And let's see what happens if we actually package the BMI alongside the binary library. The first thing is obviously word of caution is that the compiler documentation, and specifically for both GCC and Clang, it says that BMIs are not compatible across compilers because they're different file formats altogether. They may not even be compatible, and actually they're more likely not compatible across different versions of the same compiler. And additional things, especially clients will tell you, is that even if on the same version of the same compiler, they will not be compatible with using different compiler flags, right? So this is something to keep in mind. And this is actually a departure. When we consume libraries with a library file like a libfmt.so and header files, we expect this, at least in Linux, if they're ABI compatible with a standard library, it doesn't matter what compiler I'm using on the other side, right? I could use Clang or I can use GCC and it would work. If we entertain the idea of reusing the BMIs, we're actually adding a constraint to that, which tells us, no, you can only use this BMI with the specific compiler, the specific version. So this already doesn't sound like the right thing to do, but I still tried. And yeah, the documentation here, I think for GCC is very specific. Consider this a rebuildable cache artifact and not something that you would distribute. I'm very stubborn, so what I thought is, because I work with a content package manager, and I thought I'm going to do an experiment where if the constraint is the compiler and the compiler version, I can already model different packages depending on the compiler and the compiler version anyway. So I could theoretically bundle BMIs and give it a go. And this actually did not work, and I'll show you why. How does this work on the consumer side? Well, we already have ways of telling the consumer, hey, if you're consuming these libraries, your consumers should have this, should use these compiler flags on the consumer side, right? So for MSVC, that's what it would look like. For Clang, there's something similar. GCC I was not so lucky, but we already have abstractions for this. The interfiles compile flags in CMake, if you have an imported target in CMake, this is what you would use to achieve this. There's also different ways, like package config has the C flags as well. This is like, okay, these are the flags that your consumers need to be built with in order to consume this library. So I gave this a go. I created kind of packages that had the BMI and the library file with a compiler flag like that. And in CMake, I created an imported target. So fmt : fmt is an imported target. And I just manually typed that last line there into files compile options. If you are consuming this with MSVC, please use the fmt.ifc, which is the BMI generated by MSVC on the consumer side, right? And this worked actually, right? Because I could guarantee that I was using exactly the same version of the compiler to do it. But I was not so lucky with others. So then I tried, okay, I'm going to do a content package, and I'm going to express the same information such that content propagates the flags, and that's what happens with Clang. Instead of passing the / reference, I tell Clang, the module file for FMT is here relative to the package folder. And this could potentially work. Of course, it doesn't support GCC, but then it didn't work. And the reason it didn't work, and this is something I mentioned earlier, which is in the documentation of Clang actually, the FMT build scripts, when you're building the share library, it passes the visibility hidden flag when it's compiling it. And then the BMI, when you're building the library, is going to have this embedded in the BMI information, but when you're consuming the library, you're not supposed to have the visibility hidden past to your file. So Clang is telling me the BMI was generated with a different visibility flag than the file that you're building now, right? So this is the consumer side. And this is just an example of the many, many ways in which Clang will not accept a BMI that was previously generated unless the compiler flags actually do match. And when you think about it, it's actually very common when you're dealing with libraries that you're distributing that they're built with different flags. We see this in Windows all the time. If we have a shared library in Windows, we typically, we have those macros for the API decorators. So when you're generating a library, they're supposed to have one value, but when you're consuming the library, they're supposed to have another value. So that's no longer the case with BMIs because all that information is included in the BMI file. Although for that particular case, MSVC was actually a lot more forgiving. And well, this is just a highlight of an example of the visibility problem. So now this is the documentation for Clang, right? The wording is very similar to the documentation for GCC, which is modules are envisioned as a cache. So the BMIs are not supposed to be distributable artifacts. And not only that, but even within the same project, if in your same project you're using different flags, and I'll show you an example later, it's unlikely to work. So, and another word of caution, this is the case for both Clang and GCC when it comes to incompatibility with BMIs. But for MSVC, it looks like they, at least Gabriel Dos Reis says that this was a thread on Reddit, that they put no restrictions on sharing BMIs. And in fact, this is something that they want to support. They have actually open sourced the file format of their BMI that's used internally by MSVC, I think with the hopes that other compilers adopt it. So at the moment, on the standard says that the BMIs are implementation defined. And at the moment, I think the implementation that most vendors have adopted is that it's just the internal representation, binary representation that is just mapped and deserialized on the consumer side just for speed. But the implementation could also be in a way that allows reusing these artifacts. That's not the case today. It may be the case in the future, so we have to continue watching the space. And this was another issue that I tried. It's very common when you have a pre-built library that you build it on one machine, it could be a CI machine, and then you use it on a different computer altogether. So I thought, okay, I'm gonna, with Clang, I'm gonna bundle the library and the BMI, and I'm going to consume it on a different machine. What happened was that Clang needs the source file from which the BMI was generated to be present in a path that exists on the consumer side. So it wasn't even a case of the compiler flags were mismatching. It's like Clang needs the specific file. And why would Clang need this file? I'm not sure it's strictly required, but if I'm calling the functions wrong and it needs to show me a compiler error, it will typically show me where, like, reference the original file. And if I don't have this file, it's referencing a file that I don't have. So for error reporting purposes, I think that's also important. This was not a problem with MSVC. So MSVC did not require the file to exist. However, if I forced an error situation where the file was not in my computer, it will sort of report an error in a file that is just not there on my machine anymore. So as a recap, when it comes to having a package mechanism where we have the library file, whether it's libfmt.so, the A or the Windows equivalent, and the BMI, everything points that we shouldn't be doing this. With GCC, it's not even easy to tell GCC, hey, for this module, use this file, but that's a different story. And then Clang is very, very strict, more so than GCC and MSVC. And for the Visual C++ compiler, it's unclear at the moment what the BMI compatibility model is. I did find it to be a lot more forgiving, even across the same build with different flags. But the documentation does mention that the compiler flags do need to match in order to reuse the BMI compiler elsewhere. So, which brings us to, if bundling the BMI is not a good idea, we should bundle the file from which the BMI is compiled. And bear in mind that this file does not need to have implementation. It could just be declarations. but this does impose change in how we do things. Is that it's no longer just a case of propagating a compiler flag. It's no longer just a case of propagating an include path to your consumers. Now our build system needs to know that it needs to build that file, and it may not need to compile the file fully and produce the object file. It only needs to generate a BMI for it. Compilers do have a way, I mean, most of them do, to only generate a BMI given a specific module interface unit. And that's a new capability that at the moment we don't necessarily have other than in CMake, which is, I've been given this, you need to be aware that that file needs to be compiled. And the idea is, and CMake does support it, is that CMake knows that it needs to involve this file in dependency scanning. And if there are any consumers that do import FMT, it will create a synthetic target on the fly, one that you don't see, where the BMI is being produced, and it will reorder the build order, and then everything will happen. If you don't have, this is something I didn't try, if you don't have any files that import FMT, it probably will not build fmt.cc, but will still query this file for which modules it exports. And this is supported, as I mentioned, in CMake 328, which was released back in December. And before that, Build 2 actually had a way of reasoning this by putting a special field in package config files. So the extension would be .pc, which did not rely on dependency scanning, and I think it relies on a fuzzy search and naming conventions as well between the name of the module and the file name as well. So for CMake in particular, what this looks like when you do a make install with CMake, causing CMake to generate the config files for FMT, the importable FMT. This would be a file that you bundle with your binaries. So now you bundle the FMT library, the binary file, the CMake configuration file, and you also bundle this file that is mentioned here at the bottom, which is fmt.cc, which is the file that does export FMT module. So on the importer side, CMake will parse this file, and from the information, it will actually involve the fmt.cc in dependency scanning, and then everything will work. The good thing about this is that as a consumer of this, you don't have to worry about this. This happens under the hood. Obviously, the people that do need to worry about this is the FMT maintainer, because they need to mark that file as a C++ module. And also, well, the people involved in CMake and Ninja. But the goal is what I mentioned earlier. We have a project that does what we did today: find package FMT, targeting libraries FMT, and we move from include to import. And everything, ideally, it will work as expected. So just let me show you an example. This is what I'm packaging, and that's my consumer that's elsewhere. So like I said, I packaged these two files and the CMake metadata. On the consumer side, the compiler will be invoked to generate the BMI for FMT before the compiler is invoked to translate importer.cpp. It will generate importer.o, and then we will link again the FMT library, and this will work, right? And nothing, this build order is implicit, and it will happen, and you don't have to do anything. The compiler is invoked in a way where we tell the compiler there's no need to generate the object file. There's no object file to be generated here, and those are the flags that CMake is going to add to the compiler when generating BMI. So this is good. Why? I showed you examples earlier where if the BMIs were shipped with the library, things didn't work. The visibility flag, or I built it on one computer and consumed it on another, the limitations with the compiler version and the specific compiler as well. So by generating the BMIs locally on the important side, we're increasing the chances of compatibility. And I'm being careful here because I'm saying increasing the chances. It does not guarantee that it's going to be compatible. And I'll show you an example later. And what this means is that what we now refer to as the usage requirements of the library, they need to change. The usage requirements are no longer pass a compiler flag to the consumer side, pass an include directive -I telling the other files where to find header files. This now needs to be dealt with at the build system level, but fingers crossed, the users don't have to worry about this. So we need to keep in mind there's no standard way of describing a package or even a library yet. So what we have is instead of papers trying to work out what's the best way for libraries to advertise that they have a module that is importable, and also which file has the export statement so that this file can become part of the dependency scanning on the consumer side. The last bit that I wanted to mention is we are packaging obviously fmt.cc because it does export. We are packaging the CMake configuration file. We package the compile library. Do we need to also bundle includes, right? And it depends. If fmt.cc requires to include files in order to generate that file, then yes, and that's actually the case at the moment. It may also be the case that we want to support consumers to be able to do both include on some translation units and import FMT on others if your project is not able to do this. This does require some specific linking situation in the FMT library because all the symbols are attached to the module, so they're going to have to undo that if they want to support that. And I think I saw a different case. I'll show you later, where maybe you have files that contain macros for your consumers to use. Bear in mind that import will no longer make macros available after the statement. So if you actually do need macros, then you may want to do this. But if you're not in any of these cases, then you don't need to bundle header files at all if you want an importable only library. And the last bit that I want to mention is a lot of library maintainers, they only give you header files, right? They don't want to concern themselves with like building a library, maintaining a build system, checking like supporting different compilers, platforms. They just say these are the files. In some cases, if we're dealing with templates, it could be just completely justified. In some other cases, I think it's done precisely because the package management situation in C++ is less than ideal. So they say, okay, this is the easiest way. Just copy this file somewhere, just pass the flag to the compiler, and everything is taken care of, right? You don't have to worry about building them beforehand, making them available or something like that. So the case is such that in Content Center, last time I checked, roughly 1 in 4 recipes in Content Center were for header-only libraries. And I would say there's a lot of incentive on the maintainer side because they're perceived as easy to integrate. But module-only libraries, if we can refer to such a thing, they're a challenge because the compiler needs to be invoked for the files before compiling the files that do the inputs, right? As we've seen before. So how do we do this? Who is in charge of telling the compiler, hey, you need to compile this file? So we're going from a place where we don't have any extra steps other than drop this file somewhere, the header files, and now we have an extra step of, it doesn't matter that you've only given me sources, this needs to be compiled somewhere. And how is that done? So let me show you an example here. And I showed you earlier, if I have a library that actually has a library file, a binary library file, right? I can only generate a BMI and discard the object file. But if I have a module-only library where that isn't generated, that file needs to be generated and it needs to be linked or at least visible when linking the final executable. So what do we do? If I was given only fmt.cc, what do we do? And we have 3 options actually, which I should have mentioned. It could be a static library, it could be a shared library, or it could be an object file that I keep around and just link it at the very end. And at the moment, this question doesn't really have an answer. I can show you an example of how it's done in the library in particular. But we only have source files. We may have compiler flags if in order to produce the BMIs of the object files, we need to pass specific, define specific macros or specific flags. And we may have headers, as I said before, maybe the module interface unit do inclusions of some things. So how do we proceed? And let me show you what the Vulkan HPP library does at the moment. So Vulkan HPP is a header-only library, and on the right you'll see the instructions on how to use it with the hash include statement, and that's just the one sentence that they have in their in the documentation. But they also now give you the ability to consume it as a module. So the instructions for that, they're a bit more involved. They're no longer just one line. So all of this is just scrolls to the end, and well, there's a reason for this. There's a lot of unanswered questions. There's limited compiler support. It's specific to CMake because CMake supports dependency scanning. And they also, at the very end, they give you, well, if you want to do it in the command line, this is what you have to do. So it's no longer drop these files here, pass the -i flag, and just do hash include and everything will work. It's like the compiler needs to be invoked. To translate vulkan.cppm, it will generate 2 files. And the vulkan.bmi, the BMI file is going to be needed by all the importers, and the vulkan.o that is going to be generated out of this needs to be somewhere, either in a library, static or shared, or the object file needs to be propagated to the end. So what they advise at the moment is that you call find package vulkan, which is going to give you a target that only has the header files, if I'm not mistaken, that you define yourself an add library. So that's actually going to be a static library by default in CMake, or a shared library if you enable shared libraries, and then just actually compile that file. And we're also telling CMake that this includes C++ modules, so it's going to do dependency scanning for them. And then you have to, there was more, you have to define some macros if you want, because you can no longer influence the included files with a macro when you're importing modules. So you have now to express this in the target compile option. So I just left that bit out. So this is actually going to work, but it's a bit problematic. If we have multiple dependencies in our project that are using Vulkan HPP as a module, we could have potential problems. Let's say we're using apps directory and all of the targets are visible by CMake. What if 2 different places in the CMake project use the same target name because they're just following the instructions by Vulkan? We're going to get a CMake configuration error because the target is already defined. What if they choose to do a different name? Then we're going to have the same symbols potentially in different libraries that may cause duplications when in the linked executables. So I still think that while this works for a single consumer, it may not be the solution. So I think the question of module-only libraries is still very open-ended. We don't know how it's going to look like, but we do know that the easy days of just copy some file somewhere are no longer there, unless, and I could sort of venture a guess, if there's some metadata associated with those files, this happens without you having to worry about it. But I'm still a bit worried about the possibility of the symbols ending in multiple libraries, multiple places, and ODR violations as well. So we'll see how that goes. So based on this, I think this really shows that we are going to need to bundle the library files as we have been doing in the past, and the the module interface units, the module interfaces, which are source files, and that the build system needs to have the logic to just generate the BMLs on the fly when they're needed. Now, going back to something I mentioned earlier, that this was the optimal solution to increase the compatibility chances of the BMI. Let me show you some examples where this may be a little problematic. So this is something that's actually really good now. Let's say I build FMT with C++20. And obviously, when building a library, the compiler is going to generate both those files, and I will link or add the FMT object into leave.fmt.a. And then these green, highlighted in green, are the files that are bundled to my consumers. And then I'm a consumer of C++23. What's going to happen is that the build system is going to generate the BMI with C++23, and that's actually going to work. Whereas, as I showed you earlier, if I had shipped the FMT BMI that I generated when I generated the library, it would have been completely incompatible with C++23, at least if you're inclined, right? So that's actually a good thing. This will work. This is actually the advantage of having the build system on the importing side generating this file here. Now, and I think what was this? Let me see. Oh yeah, sorry. This is a way of showing exactly that if you had bundled the BMI and the C++ standard was different, this is the error that you're gonna get. So as I said, getting the BMI on the consumer side is what's gonna work. And then here, and this is something I was using some of the module libraries that Daniela was using. I think it was last year actually at this conference, where all of those were libraries that had modules. And I had a really interesting problem, is that on the consumer side, it was telling me, and bear in mind that I'm not bundling BMIs with the libraries or consuming them externally. They're all part of my project, right? They're all built locally. So I would assume, okay, I'm building them locally, so I have the same compiler, the same compiler version, allegedly the same compiler flags, and it still didn't work. And I had, let me show you. I have my app.cxx that was doing all of these imports, and all of them were part of the project. And then, in particular, the argparse target, it required the size deallocation flag, which was a public Taran compile option. And if you're familiar with CMake, this causes my app, when I link against argparse, to also add that flag. So we think, okay, this is working, right? Argparse needs to be compiled with size deallocation. And if you're using argparse, CMake will make sure that you're also compiling with this flag. But the error I was getting, and this is very, very interesting, is that CMake will cause my app to be built with that flag, as well as the argparse when generating the BMI. But CMake will not cause all the others to have the flag. So Clang was complaining that the BMIs will build with different flags. So we're not only dealing with like the compiler flags to generate the BMI for the module need to match the importer. They need to be coherent, at least for Clang at the moment, coherent across all the ones that you're importing. And I didn't find any solution to this other than globally passing the same flag via CMake to all the targets in my project. So at the moment, even using modules, this is one of the tricky and hairy areas of using the BMIs, even if they're all generated locally. So while dependencies can give us a correct bit order, it may be difficult for the build system. The build system doesn't know whether some flags are compatible or not. And to be honest, there's a chance that Clang is too strict. There's a chance that there's an if statement software that they can relax the condition and everything will still work. And as I saw with MSVC, so like this is something that the community is going to have to see and evolve. But the consequence of this, there are going to be cases where the BMIs have 100% need to be regenerated for different compiler flags. I think a good example was building in C++20 mode and C++23 mode. So here what's going to happen is that for some cases, the build system may have enough information to actually generate two BMIs for the same module to be used in two different imported places. Now, if we go back to what I mentioned earlier, that there were advantages in compile times, because we're going from parsing the same include in multiple files in parallel at the same time and doing the same work. Well, there's a chance that if you had different compiler flags across those files, you were doing almost the same work, but not exactly the same work. And the compile time benefits, it may actually be different if you have to generate different BMIs for each importer. So I still think there will be definitely compile time benefits. There's a lot of teams that actually have full control of the compiler flags across the entire project. So if they do that, they're not going to face this problem. So I don't think we're going to be in the worst case scenario where you're going to need as many BMIs for the same module as translation units doing an import, but that could still happen. And the last bit that I want to mention, we only have a few more minutes, is that we all face this, that errors related to dependencies are really frustrating. The build system can fail, the compiler can give you an error, the linker can give you an error, and the worst is the runtime errors that have no explanation. So generating the BMI, locating the BMI, and loading the BMI are already mostly solved by dependency scanning. So errors related to that are less likely to happen. But today we still have errors when using modules, and I think anybody who does use modules either as a library maintainer or as a consumer, I think I've seen MP units is not compatible with MSVC, even though it uses modules. The Vulkan headers as well, they say that there's a specific bug in Visual Studio, so it cannot be used with Visual Studio. If you've used GCC, I experienced a lot of internal compiler errors as well. Those are easy to reason that it's a compiler bug. But there's some errors that you don't know whether it's a compiler bug, it's a library bug, because there's something that they haven't done right with the module interface unit, or I don't think this is the case, or if it's an issue with the importer. So just to show you some examples here. Well, let me see. What was the error here? This error, it was an internal compiler error, and for FMT, what I've seen with GCC is that if you're importing and you're not using any optimization, so you don't pass minus 01, OG, O2, or something like that, the compiler is going to crash, right? This has been reported, but it just really shouldn't fail. But at least you know, okay, the compiler needs to solve this. Let me see here. There was another error as well with GCC, although I believe this has been fixed, and it affected an earlier version of FMT. On the importer side, if I do import FMT, it didn't work. If I did include the locale header before doing import FMT, which should bear no difference, but it happened, then it did work, right? And the error was very, very confusing to me, but it was also confusing to the compiler. Like, and I mean, if the compiler is confused, then I'm completely helpless as to how to fix this. And then you may also get linker errors as well. All modules have a module initializer that may be empty and may actually not do anything, and that's part of the reason why the object file needs to be somewhere likely or hopefully inside the library. But I was getting this linker error, and if I'm using FMT 11 that was just released the other day with GCC, if I build it as a shared library, I get linker errors that aren't related to anything that I don't get when it's built as a static library. So that was a bit frustrating, because I thought, oh, GCC finally works, but it was not the case. So some conclusions: slowly more libraries and library maintainers are adding module support for the libraries. And I think, honestly, I would encourage everyone to at least try. We're not going to get results if we don't actually try and report the bugs to the relevant maintainers. Dependency scanning, it works really well. It solves build order issues, although it requires, at the moment, a very recent CMake, recent compiler versions, and or building all your dependencies as part of the same project. CMake 328 supports modules in imported targets, but that only works for CMake. We still don't have a standard way to interface with other build systems, and as we've seen, we do have issues with BMI compatibility, even in the same project, even if everything is bundled and built together. Can package managers help? I would say they could help if you have full control of how your dependencies are built. You can sort of force the same compiler frags across everywhere, the same C++ standard, and that can increase the chances as well. And if you're using MSVC, you're actually maybe able to reuse the BMIs. But otherwise, little help. I think at the moment, the ball is in the court of compiler maintainers and build system maintainers. And there's still many open-ended questions. The object file is produced by the translated module interface. The examples that I've shown you with FMT, I linked or included the object file in the FMT library. That's not the case for the import std. library. So if you're using Clang, libc++ does not include the module initializer in libc++, so you have to find a way to link it externally to that. I think what the CMake maintainers have done is just add it to a static library that gets created on the fly. And also the object file produced by the translated module interface, when you're only given a module, you have a choice of static library, shared library, or an object file as linked at the end. We need something that goes beyond CMake, and we need module metadata for pre-built libraries that don't require only CMake, but can actually be reused by any other build system. Questions around module-only libraries, if they're practical, and how can we get something equivalent to what we had before, which is the developer should not worry about this, right? And I think one of the biggest challenges is going to be the logic to regenerate the BMI, even multiple BMIs for the same module, depending on the compiler flags that you use across your project. So that's it. Thank you so much.